Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just transport yourself to a very specific moment in the not-so-distant future.
Okay.
Picture yourself on a Friday night, specifically Friday, April 13th, 2029.
The classic Friday the 13th.
Right, exactly. So you step out your back door, maybe there's like a slight chill in the air, you have a jacket on, maybe a cup of coffee in your hand.
Sure, that's nice.
Yeah, and you look up at the night sky. And there, just moving visibly, steadily across the darkness, is a massive object.
And we're not talking about a little streak of light either.
No, you don't need a telescope, you don't need binoculars, you just need your own two eyes to witness, essentially, a mountain hurtling past our planet. We are talking about the asteroid Apophis.
It is, it's a really profound image to consider, especially when we, scale it properly in our heads.
Yeah.
Because in that scenario, you are looking at a rock that is roughly 375 meters across.
Which is huge.
It's massive. That is not a shooting star burning up in the upper atmosphere. That is an object with the mass of a modern aircraft carrier. Or like the height of the Empire State Building, just coasting through the void right in our orbital backyard.
It's just wild to think about.
Yeah, and to see something of that immense scale moving in real time against the backdrop of the fixed stars, I mean, it'll be a visceral reminder of the dynamic, sometimes really violent solar system we inhabit.
Totally. And let's establish the most critical fact immediately, because the date, Friday the 13th, combined with a giant asteroid, sounds entirely like the setup for a disaster movie.
Oh, yeah. The media field day is going to be intense.
For sure. But there is absolutely zero risk of impact in 2029.
Zero.
We know its trajectory. It is not hitting Earth.
Right.
So it is going to skim past us in a way that is so incredibly rare. It is like mobilizing the entire global scientific community.
It's a once-in-a-lifetime, actually. Many lifetimes opportunity.
Exactly. So we are looking at this monumental international effort to literally chase this asteroid down.
We're going after it.
We are. And today, we're going to examine the Ramses mission, the unprecedented alliance between Europe and Japan making it possible, and, what this incredibly close shave means for the actual applied science of planetary defense.
Because this event, it really alters our entire approach to near-Earth objects.
It changes everything, right?
It really does. The shift in perspective here is foundational, because for the entirety of human history, our relationship with asteroids has been remote.
Like, very distant.
Right. We find them as faint pixels on a telescope sensor, or, we spend a decade planning to launch a highly specialized probe deep into the quiet isolation of the solar system, just to get a brief look at one.
Just a quick flyby.
Exactly. But Apophis in 2029 inverses that entirely. The cosmos is coming to us.
It's delivering it right to our front door.
Delivering a pristine relic of the early solar system right to our doorstep. And the logistical, the engineering, and the scientific ambition required to meet it and to launch a companion spacecraft to observe it up close during this flyby, it just demonstrates an incredible maturation of our capabilities as a spacefaring species.
It really does. So let's break down the mechanics of this cosmic close shave, because the numbers here are just staggering.
They are.
We established the 375-meter scale, but the proximity is what makes this historic. Apophis will pass just 32,000 kilometers above Earth's surface.
Which is incredibly close.
Right. Now, 32,000 kilometers might sound like a vast distance if you're driving a car, but in astronomical terms, it is a hair's breadth.
It's nothing.
That is less than 1/10 of the distance to the moon.
Yeah.
And what really puts this into perspective for me is that it is closer than our own satellites in geosynchronous orbit.
That altitude is a highly specific and sensitive zone.
So explain that, because that sounds terrifying.
Well, geosynchronous orbit is about 35,786 kilometers above the equator. We put telecommunications satellites, weather monitors, early warning defense systems there because at that specific altitude, a satellite's orbital period perfectly matches Earth's rotation.
It essentially just hovers over one spot on the globe.
Exactly. And Apophis is coming in at 32,000 kilometers. It is slicing completely inside that multi-billion-dollar ring of infrastructure.
Which immediately raises a red flag for anyone visualizing this.
Sure, of course.
If you have this ring of vital satellites and a 375-meter rock plows through the middle of it at incredible velocity, I mean, the instinct is to worry about our orbital infrastructure.
Are we going to lose our GPS, right?
Yeah. Like, are we talking about a cosmic bull in a china shop? Are we going to lose global communications? Is this going to trigger a cascading debris event up there?
It's a completely logical concern, but it stems from a misunderstanding of the volume of space.
Okay. How so?
We often visualize orbital rings like lanes on a highway just packed bumper to bumper with metal.
Like the rings of Saturn or something.
Right. But the reality is that space, even near Earth space, is profoundly empty.
Okay.
Yes, Apophis is crossing the orbital plane, but the distance between individual satellites in the geosynchronous belt is typically hundreds, if not thousands, of kilometers.
So it's not like threading a needle through a crowded room.
Not at all. Furthermore, orbital dynamics isn't a game of chance. Astrometric radar tracking has mapped Apophis's trajectory down to the kilometer.
They know exactly where it's going.
Exactly. We know its orbital inclination, its exact velocity, and the specific keyhole of space it will occupy at every single second of the flyby. It will pass safely through the vacuum without coming anywhere near a satellite.
So the danger to our infrastructure is essentially zero, even though it feels, uncomfortably close.
Right, zero danger.
But I want to talk about how rare an approach like this actually is, because asteroids fly by Earth all the time.
They do.
We read the headlines every month about some rock passing us.
Yeah, why is Apophis different? The difference is the intersection of extreme proximity and massive scale.
Okay.
We have small rocks, objects maybe a few meters across, pass us frequently. Often they burn up in the atmosphere as bolides or fireballs.
Right, shooting stars.
But an object 375 meters in diameter, coming within 32,000 kilometers. Statistically, an event of this magnitude occurs only once every 5,000 to 10,000 years.
Wait, let's pause on that. Once in 10,000 years.
Yeah.
If we rewind the clock 10,000 years to the last time an object this massive got this close, what were we even doing?
We were a completely different species in terms of our societal development.
I mean, that's practically the Stone Age, right?
Literally. 10,000 years ago marks a transition from the Pleistocene to the Holocene epoch. The great glaciers of the last ice age were just retreating.
Wow.
We are talking about the dawn of the Neolithic Revolution. Human beings were just beginning to experiment with agriculture in the Fertile Crescent.
So farming was barely a thing.
Barely. There were no cities, no written languages, no metalworking. If an asteroid of this size passed that close to Earth back then, our ancestors might have looked up from, newly planted fields, seen a bright point of light moving unnaturally fast against the stars, and had absolutely no astronomical framework to comprehend what it was.
It would have just been pure myth and mystery, like a god walking across the sky.
Completely. And fast forward to April 2029, and the contrast is just mind-bending.
Because not only do we know exactly what it is, but up to 2 billion people across Europe, Africa, and parts of Asia will be able to walk outside and track it with their naked eyes.
The viewing geometry is exceptionally favorable for this pass.
How does that work?
Because of the trajectory and the time of day it makes its closest approach, a massive swath of the populated globe will be in darkness, which provides perfect viewing conditions.
Think about the sociological impact of that for a moment.
It's going to be huge.
Right. If you are listening to this right now, in 2029, you are going to participate in a shared planetary event.
A collective experience.
Yeah. A quarter of the human population looking up at the exact same time, watching the same rock.
It's rare.
In an era where we are incredibly segmented by screens and time zones and borders, having a singular unifying cosmic event visible to the naked eye it's powerful.
Yeah.
It reminds us that we are all riding the same rock through a very busy solar system.
The cultural impact will be significant, absolutely. But for the international scientific community, the philosophical beauty of the moment kind of takes a back seat to the physics.
Oh, I'm sure. They're probably drooling over the data.
Oh, they are. This isn't just a celestial light show. Because Apophis is getting so deep into Earth's gravity well, it is going to be subjected to immense physical forces.
Right.
And that is what makes this the opportunity of a millennium.
So let's dive into the physics of that flyby, because this is where the science gets deeply strange and fascinating to me.
It really does.
When you say it's getting deep into the gravity well, we're talking about tidal forces, right? Earth's gravity isn't just pulling the asteroid off its path. It's going to physically warp the asteroid itself.
Exactly. To understand how Earth is going to reshape Apophis, we have to look really closely at what tidal stress actually is.
Okay, break it down for us.
Gravity is not a uniform field. Its strength decreases with the square of the distance.
Meaning the farther away you are, the weaker the pull.
Right. So Apophis is 375 meters across. When it is 32,000 kilometers away from us, the side of the asteroid facing Earth is technically a few hundred meters closer to the center of Earth's mass than the far side of the asteroid is.
Oh, I see. Which means the gravity pulling on the bottom of the asteroid, the side facing us, is measurably stronger than the gravity pulling on the top.
Exactly, and that gravitational differential creates tension.
Like it's being pulled apart.
Yes, it's the exact same mechanism that allows the moon to pull Earth's oceans into high and low tides, just on a much more acute scale given the proximity and the solid nature of the bodies involved. Earth is effectively going to stretch Apophis.
Like an invisible pair of hands kneading a giant rocky ball of dough, or a massive magnet pulling apart a cluster of iron filings. We aren't just watching it fly by. We are watching Earth give a deep tissue massage.
I like that analogy. Nature is essentially conducting the experiment for us.
But wait, Earth's oceans are liquid. They flow easily, so tides make sense. Apophis is a rock. How does a mountain of rock stretch without just shattering? Or does it shatter?
Well, that depends entirely on its internal structure, which is actually one of the primary mysteries we are trying to solve here.
Really? We don't know what's inside it?
Not exactly. In the early days of asteroid science, we assumed these bodies were solid, monolithic chunks of iron, or silicate.
Like a giant boulder.
Right. And if Apophis were a solid monolith, the tidal forces would cause it to groan, perhaps inducing seismic quakes that would ripple through the solid rock.
Asteroid quakes.
Exactly. But our recent missions to other asteroids like Bennu and Ryugu have shown us that many of these objects are not solid at all. They are what we call rubble piles.
Rubble piles. So basically a collection of gravel, boulders, and dust held together by their own incredibly weak mutual gravity.
Yes, millions of distinct fragments just clinging to one another in the dark.
That's so creepy to think about.
It is. The gravity on these rubble piles is so microscale that forces we ignore on Earth, like van der Waals forces, actually play a major role.
Wait, van der Waals forces. Remind me what that is.
It's the slight electrostatic attraction between molecules, or in this case, between grains of dust. It's what allows geckos to climb walls.
Oh, right. So dust is basically just statically clinging to other dust.
Exactly. That plays a huge role in holding the entire asteroid together. So when a loosely bound rubble pile like that enters Earth's gravitational grip at 32,000 kilometers, the tidal stress can easily overcome those extremely weak cohesive forces.
So if you're looking at this with a high-powered telescope, what are you actually seeing happen to the surface? Is it pulling apart?
We expect to see the surface undergo radical alteration. As the tidal forces stretch the body, boulders might become dislodged.
Just floating off.
Or rolling. We could see localized avalanches where gravel and dust slide down the microgravity slopes of the asteroid, exposing fresh, unweathered material from beneath the surface.
Oh, wow.
Furthermore, the gravitational interaction will likely torque the asteroid, changing its spin rate.
It'll make it spin faster.
Or slower. Or change its axis. It currently tumbles through space in a complex, non-principal axis rotation, kind of like a wobbly football.
Okay.
Earth's gravity could alter that spin, which in turn creates centrifugal forces that might cause the asteroid to bulge at its equator. We are quite literally letting Earth's gravity conduct a deep tissue physical exam of this object.
Which is such a brilliant reversal of how we normally do space exploration.
It really is.
Usually if we want to know what's inside an asteroid, we have to spend a decade building a probe, launching it, flying it for millions of miles, and shooting a projectile into the rock.
And that's if everything goes perfectly.
Right. But here, the solar system is delivering the asteroid to our laboratory, and Earth itself is the testing apparatus.
Perfectly.
But I want to push back on the necessity of this for a second.
Okay, sure.
It's undeniably cool physics, right? Like watching a rock get stretched. But if we already know Apophis isn't going to hit us, why is it so critical that we measure every single pebble shifting on its surface? Why are we treating this like an urgent planetary defense mission?
Because planetary defense relies entirely on understanding how asteroids react to kinetic stress. And right now, our data is severely limited.
We just don't know enough.
Exactly. Imagine a scenario 20 years from now where we discover a 400-meter asteroid that is on a confirmed collision course with Earth.
Okay, terrifying, but go on.
Our primary defense strategy is kinetic impact.
Which means?
Flying a heavy spacecraft into the asteroid at high velocity to slightly alter its momentum, pushing it off its collision course.
Ah, the billiard ball method. Just smack it out of the way.
In theory, yes, but the reality is vastly more complex. If you hit a solid monolithic block of iron, the momentum transfer is highly efficient. The rock moves predictably.
Just like hitting a cue ball.
Right, but what if that asteroid is a rubble pile with high macroporosity? What if it's mostly empty space inside?
Oh, I see. Then hitting it with a spacecraft would be like firing a bullet into a sandbag. The sandbag just absorbs the energy. It doesn't move.
That's a great analogy. It absorbs the kinetic energy, or even worse, the impact shatters the weak, cohesive forces holding the rubble pile together.
Oh, no!
Yeah. Instead of one large asteroid on a collision course, you have just created a shotgun blast of 100 smaller, deeply destructive fragments.
Like a cluster bomb.
Exactly. All still heading toward Earth's atmosphere, but now completely impossible to deflect.
Because you can't hit 100 different rocks at once.
You can't!
So we desperately need to know the structural integrity of these things before we ever try to hit one.
We have to know the anatomy of the threat. We need to know the yield strength, the porosity, and how the internal friction of the boulders absorbs kinetic energy.
And Apophis is giving us that data for free.
Well, not for free, but it's presenting the opportunity. By watching how Apophis behaves when subjected to the maximum tidal stress of Earth's gravity, we gain invaluable empirical data on how a 375-meter rock holds itself together. It acts as a proxy for any future threat.
But the catch is, we can't get that data just by looking at it from our backyards.
No, binoculars won't cut it.
Right. Even our best ground-based observatories can't resolve the granular shifting of dust on an object moving that fast, 32,000 kilometers away.
It's moving too quickly, and the details are too fine.
To actually measure the reshaping of the asteroid, to see the before and after of this gravitational stress test, we need an observatory right next to it, which brings us to the logistics of actually intercepting this thing.
And this is where the engineering reality meets the scientific ambition.
Yes. Let's talk about the Ramses mission.
Right. To maximize this opportunity, we need a spacecraft to rendezvous with Apophis before the April 2029 close approach, fly alongside it during the flyby, and remain with it afterward to measure the permanent alterations. Enter the Ramses mission.
The Rapid Apophis Mission for Space Safety. Ramses.
That's a great acronym.
It really is.
Yeah.
But the timeline here is what absolutely baffles me.
Sure.
The plan is to launch Ramses in 2028, to arrive before April 2029.
That's right.
Now, historically, deep space missions take 10 to 15 years of development, testing, and bureaucratic maneuvering before they ever sit on a launch pad.
Oh, easily. Sometimes longer.
But Ramses is being pushed through at a blistering pace.
Unprecedented.
And the way they're achieving this speed is through a newly solidified, deeply integrated alliance between the European Space Agency ESA and the Japan Aerospace Exploration Agency JAXA.
The geopolitical and administrative achievements of Ramses are honestly almost as impressive as the flight dynamics.
How so?
Well, you cannot spin up a bespoke deep space mission in 24 to 36 months if you start from scratch. The traditional procurement and supply chain bottlenecks would make it impossible.
It just takes too long to order the parts.
Exactly. The only way to meet the unyielding deadline of celestial mechanics, Apophis is arriving in 2029 whether we are ready or not.
The asteroid doesn't care about our paperwork.
It doesn't. So the only way to meet it is to leverage existing flight-proven partnerships and distribute the engineering load.
And the foundation of this was formalized recently. On May 7, 2026, they signed a Memorandum of Cooperation, along with a dedicated agreement specifically for Ramses.
Yes.
And they did this in Berlin, at the Embassy of Italy, which is an interesting geographical mix for a European-Japanese agreement. Why there?
The location highlights the pan-European industrial base that ESA relies upon. ESA selected OHB Italia as the prime contractor to build the Ramses spacecraft. OHB Italia has significant expertise in rapid satellite integration. Hosting the signing in Berlin, in collaboration with the Italian Space Agency, signifies the deep, multinational industrial cooperation within Europe.
It's a team effort.
Very much so. And that European team is now locking together with Japan's state-of-the-art aerospace sector. It was signed by ESA Director General Josef Aschbacher and JAXA President Hiroshi Yamakawa, surrounded by the industrial leadership that will actually weld the metal and write the code.
So how are they actually splitting the workload to hit this 2028 launch window? Because I imagine integrating tech from two different continents on a rushed schedule is an engineer's nightmare.
It could be, yes. But they mitigate the risk by dividing the labor along lines of pre-existing expertise.
Meaning they stick to what they know.
Exactly. They aren't trying to co-develop new components from scratch. They are integrating fully mature technologies. ESA is taking the lead on the overall spacecraft design, the systems integration, and the deep space mission operations.
They're building the car and driving it.
Basically, they are effectively building the bus, the chassis, and the brain of the spacecraft. JAXA, on the other hand, is stepping in to provide highly specific, critical hardware that ESA would otherwise have to spend years developing and qualifying for deep space.
What specific hardware are we talking about? Like, what is Japan bringing to the table?
Primarily the lightweight solar arrays and the thermal infrared imager.
Okay, let's start with the solar arrays. Why are those so critical?
Deep space missions are severely mass-constrained. Every extra gram of weight requires exponentially more fuel to accelerate.
Right.
JAXA has developed incredibly advanced, ultra-lightweight, thin-film solar array technology. These arrays can generate the necessary electrical power for the spacecraft's instruments and communication arrays without adding the massive bulk of traditional rigid panels.
Oh, that makes sense.
By JAXA handing over a flight-ready, proven solar array system, ESA shaves years off the design phase.
It's plug and play at a multi-billion-dollar level.
Precisely. Furthermore, JAXA is providing the thermal infrared imager.
And why do we need thermal imaging for a rock?
It is the exact instrument needed to map the heat retention and radiation of the asteroid's surface.
Like how quickly it warms up in the sun and cools down in the dark.
Exactly. That thermal data is crucial for understanding the macroporosity of the rubble pile we discussed earlier. Solid rock holds heat differently than a loose pile of dust and gravel.
Oh, that is so clever. So you don't even need to touch it to know what it's made of. You just watch how it cools down.
Right. But the biggest piece of the puzzle JAXA is bringing to the table isn't on the spacecraft at all. It's the launch vehicle. JAXA is providing the ride to space aboard their H3 rocket.
Which is huge, right? Because getting a rocket isn't like hailing a cab.
Not at all. Securing a launch vehicle is traditionally one of the most fraught aspects of mission planning. Launch manifests for heavy-lift rockets are often booked out years in advance.
You can't just squeeze in.
No. And the integration of a spacecraft into a specific rocket's fairing requires extensive acoustic and vibration testing. You have to make sure the rocket's engines don't shake the spacecraft to pieces on the way up.
Right.
The H3 rocket is Japan's new flagship launch vehicle designed for higher reliability and flexibility. By JAXA committing an H3 specifically for Ramses, they instantly clear the largest logistical bottleneck of the entire mission.
It fundamentally changes the pace of space exploration.
It really does.
If two distinct space agencies can trust each other enough to just hand over major components, here's the rocket, here are the solar panels, you build the chassis, it proves that the bureaucratic red tape can be cut when the scientific payoff is high enough.
JAXA President Hiroshi Yamakawa explicitly stated that this partnership advances international efforts in the field of space safety.
Yeah.
And ESA Director General Josef Aschbacher echoed that sentiment, noting that planetary defense is inherently a global responsibility. He pointed out that Ramses demonstrates how reliable partners turn ambition into action.
Ambition into action. I like that.
And it's not blind trust either. They're building upon previous successful joint ventures like the EarthCare Climate Satellite and the Bepi-Colombo mission to Mercury. The trust is already there. Now they are weaponizing that trust to beat a ticking clock.
And I love that phrase, planetary defense is a global responsibility, because it's undeniable.
It's just a fact of life.
Right. An asteroid doesn't target a specific latitude or longitude. It doesn't recognize sovereign airspace. The atmosphere doesn't care about geopolitics.
It's not at all.
A significant impact anywhere creates a thermal pulse, shock waves, and atmospheric dust injection that affects the entire biosphere. You cannot build a dome over one country. The only logical response to a global threat is a global infrastructure.
Which brings us to a vital realization about the current state of space exploration.
Okay, what's that?
Ramses is an incredible mission, but it is purely observational.
Right, it's just watching.
It is going to ride alongside Apophis, map its surface, and watch it stretch. It is gathering intelligence. But gathering intelligence is only step one.
You have to actually be able to do something with that intelligence.
Exactly. What we are seeing now with ESA and JAXA and other international partners is the construction of a comprehensive, multi-layered architecture for planetary defense. We are moving away from theoretical white papers and entering the era of applied, operational planetary defense.
Let's look at how that architecture actually functions in reality.
Let's do it.
For so long, the public consciousness around planetary defense was shaped entirely by Hollywood Bruce Willis drilling a hole in an asteroid.
Armageddon.
Right, but the actual science is much more methodical. It starts with finding the rocks before they find us, and a massive hub for that is ESA's Near-Earth Object Coordination Center, the NEOCC.
The NEOCC is the foundational layer of the shield. You cannot deflect an object you haven't tracked.
You have to see it coming.
Right. The NEOCC operates as an international clearinghouse for astronomical data. Telescopes all over the world like Pan-STARRS, the Catalina Sky Survey, and ESA's own optical ground stations are constantly scanning the night sky, taking sequential images of star fields.
Looking for the one pixel that moves.
Exactly. It's a massive data processing effort. When an anomalous moving object is detected, that astrometric data is fed into the NEOCC.
And what do they do with it?
Their algorithms instantly begin calculating potential orbits, projecting the object's path years or decades into the future to assess the probability of Earth impact. They characterize the object's size based on its absolute magnitude, and they coordinate follow-up observations to refine the trajectory.
So they're the ones crunching the numbers.
The NEOCC is the early warning system. They are the reason we know Apophis is coming, and they are the reason we know it will miss.
So layer 1 is the NEOCC, detect and track. Layer 2 is missions like Ramses. Intercept and characterize the physical structure under stress.
Yes.
But that still leaves layer 3, the action.
The intervention.
Right. If the NEOCC finds a rock, and Ramses tells us it's a loosely bound rubble pile, and the math says it's going to hit us in 10 years, what is the actual mechanism for stopping it? How do we prove we can actually move a mountain in space?
Which is the ultimate question.
It is. And that brings us to the most aggressive part of this global architecture, the Hera mission.
The Hera mission is the necessary corollary to everything we've discussed so far. Hera is another major ESA-led initiative with critical JAXA partnership, but its objective is entirely different from Ramses.
When is Hera happening?
Hera is arriving later this year in 2026 at the Didymos asteroid system, and its purpose is to study the aftermath of humanity's first actual test of asteroid deflection.
We have to give some context to Didymos because it's a brilliant piece of orbital physics.
Very clever.
Didymos is a binary asteroid system. It's a larger asteroid, roughly 780 meters across, orbited by a smaller moonlet called Dimorphos, which is about 160 meters across.
Basically an asteroid with its own little moon.
Exactly. Now, why did we choose a binary system to test our planetary defense capabilities? Why not just pick a lone asteroid flying around the sun and hit that?
The choice of a binary system is an elegant solution to a massive measurement problem.
How so?
If you take a solitary asteroid orbiting the sun and hit it with a spacecraft, you will alter its velocity. But the change will be incredibly minute, perhaps fractions of a millimeter per second.
Which doesn't sound like a lot.
It's not, though over years it adds up. But trying to measure that microscopic change in a massive multi-year heliocentric orbit from Earth is incredibly difficult. It would take years of observation to confirm if we actually moved it.
But with the binary system, it's different.
With a binary system, you have a small moonlet orbiting a primary body very quickly. Dimorphos orbited Didymos roughly every 11 hours and 55 minutes.
That's orbit.
Very fast. If you impact the moonlet and change its velocity by that same fraction of a millimeter per second, you change its orbital period around the primary asteroid by several minutes.
Oh.
That is a massive, highly visible change that ground-based telescopes on Earth can measure almost immediately by watching the dip in light as the moonlet eclipses the larger body.
It's basically a celestial clock, and we smashed a spacecraft into it to see if we could make it run fast.
Exactly. Which we did with the DART mission.
The double asteroid redirection test.
Yes. DART hit Dimorphos and it drastically shortened its orbit. But DART destroyed itself in the process. We know the orbit changed, but we don't know exactly what the impact did to the structure of the moonlet. And that is why Hera is arriving in 2026.
Hera is going back to the scene of the crash.
Hera is conducting the vital post-impact crime scene investigation. DART proved that kinetic impact can change an orbit. But to turn kinetic impact into a reliable operational planetary defense technique, we need the exact math.
We need to see the damage.
We need to know the mass of Dimorphos. We need to measure the exact size and shape of the crater DART left behind. Did the impact just dent a solid rock, or did it deform the entire structure of a rubble pile?
Right, going back to the sandbag analogy.
Exactly. Did the debris blown back into space act as an additional thruster, enhancing the deflection?
Oh, like rocket exhaust pushing it further?
Precisely. Hera will meticulously measure all of these variables to give us a complete physical model of the impact.
The way these missions interconnect is just incredible to me. Ramses and Hera are two halves of the same survival strategy.
They absolutely are.
Think about a medical intervention. Hera is analyzing the surgical strike. It's studying the exact mechanics of how you hit an asteroid and how it reacts to blunt force trauma.
Yeah.
And Ramses is the MRI beforehand. Ramses is watching how a similar asteroid's internal anatomy reacts to gravitational stress. So we understand the tissue of the target before we ever have to operate.
That is a perfect synthesis. You need the deep structural understanding from Ramses, and you need the blunt force mechanics from Hera to actually build a working planetary shield.
It represents a profound evolution in human capability, doesn't it?
It really does. I mean, for 4 billion years, life on Earth has existed at the complete mercy of the cosmos.
Just crossing our fingers.
Pretty much. The biosphere has been routinely reset by kinetic impacts. The dinosaurs were apex predators, but they lacked a space program.
Right. They couldn't look up and do anything about it.
Now, for the first time in the history of this planet, a species has developed the technological capacity to look out into the dark, identify an existential threat, understand its physical composition, and actively intervene to alter its trajectory.
We are engineering our way out of the probability of extinction.
Exactly. We are taking control of our orbital neighborhood.
And we're doing it not as individual rival nations, but as a collective.
That's the most important part.
We are building a defense network made of tracking centers in Europe, telescopes in Hawaii, infrared imagers from Japan, and global scientific cooperation. It proves that when the stakes are literally planetary, humanity possesses the capacity to mobilize across borders.
As Joseph Ashbacher noted regarding the ESA-JAXA partnership, international cooperation remains the absolute cornerstone of our approach to space in an increasingly complex environment.
It has to be.
Ramses, Hera, and the NEOCC are concrete proof that shared intention can manifest as mission-level reality.
We have covered an immense amount of ground today, from orbital mechanics to geopolitical alliances. So let's just briefly return to that Friday night in 2029 to anchor all of this.
Sounds good.
On April 13th, an object the size of a skyscraper will fly closer to our planet than the satellites that beam television to our homes.
It's going to be a sight.
As it passes, the invisible, crushing gravity of Earth will reach out and knead the rock, shifting its boulders, changing its spin, testing its structural limits in a display of physics we have never witnessed up close.
Never.
And riding shotgun, right next to it, watching every single shudder and micro-avalanche, will be the Ramses spacecraft, born of a rapid, unprecedented alliance between Europe and Japan.
It is a historic astronomical event met with an equally historic display of human ingenuity.
So the next time you walk out into your backyard and look up at the night sky, I want you to consider what is coming.
Yeah.
When that specific Friday rolls around and 2 billion people look up to watch Apophis skim the edge of our atmosphere, it won't just be a terrifying anomaly. It will be a moment of profound, undeniable global unity.
A shared human experience.
Think about what it will feel like to stand there in the dark, watching that silent rock pass, knowing that humanity isn't just cowering below. Knowing that right beside that mountain in space, an international robotic ambassador is flying in formation, silently taking notes, learning its secrets, ensuring that the next time the universe throws a rock our way, we won't just be watching.
We will be ready.
We will be ready.